Okay, so from today, I will be taking over the lectures from Professor Chen Yuxun. She has already taught you about the uh, fundamental knowledge of robotics. For example, forward kinematics, the backward, inverse kinematics. Today, I want to share some information about path planning of robots. If we want to move a robot starting from an initial position, if I assign, I would like to move that robot to grasp this cup. Of course, I need to know the coordinate of the cup, and then I can use inverse kinematics to figure out what would be the joint angles when I move my robot in this configuration by calculating the angles, right? Once you use this inverse kinematics, you know, okay, that's my final destination. This is my initial one, this is my final one. What you need to do next is to design how you're going to move your robot from the starting point to the end point. You can move like straight, along a straight line, meaning the end effector coordinate follows a straight line. Or there is a curved trajectory. I will tell you what is that curved trajectory. Okay? Eventually, you reach to this position, and then you may have a gripper. Maybe it's electrically actuated or numerically actuated. Either way, you drive the gripper, perform the grasping, and then you take the second move. Maybe you want to pick up into a different configuration, move it somewhere else, put it down, release the gripper, go back home. So usually it's a sequence of motions. And along this sequence, it's a bunch of move from A to B. Basically, there's an A point, move to B point. You basically define where you want to move from and where you are going to move to from A to B. And you also describe, is it like a straight line or like a curvy line? And there's a reason why people sometimes would like to move along some kind of curvy trajectory. I will tell you today. So let's start with my handwriting. I'm using iPad to teach you, so I will be writing some math and make some drawings. You need to understand my English writing. So this is my handwriting of capitalized characters. They are easy to understand. Sometimes my Z looks like this. Sometimes S looks like this. Sometimes my J looks like this. Yeah, I think the capitalized one is easier. So the small one. Oops. So the most difficult one probably is R and S. Okay, that's how I write. Of course, sometimes I write R like this. S, of course, sometimes like this. So if you have difficulty understanding my written character, let me know. Okay? So let's define some symbols. So let's say this is a robot. Okay, I'm not going to draw something professional, just indicating a robot. So let's say this is the end effector. I'm gonna use P point in this lecture. And there are multiple angles. For example, this is like a theta 1. Maybe if we define things like this and so on. And we mostly work on 6 degree of freedom robot. So in today's lecture, I'm gonna use a vector of x to keep all the angles. So these are like my variables, okay, just for today's lecture. And I'm gonna call this configuration, because every position a robot stops, you can call this a configuration. Another one, okay? So that configuration is gonna be defined by the collection of joint angles, okay? And P point, you can say it's a three-dimensional point, but in fact you are controlling the coordinate attached to the n effector. So let's say the n effector looks like this. Usually it's like a circular plate. And let's say there is a coordinate. This is the n effector, okay? So that frame, if you only focus on the XYZ, then I cannot tell the difference if I spin around certain axes. So in fact, you are controlling not only the coordinate of the n effector, you are also controlling its orientation. So in fact, P is like 6 degree of freedom as well. So in this case, let's say I'm gonna use ABC to represent the angles, just for easier description. So it's like a certain angle along certain axis, I call it A, and the second one I call it B, and then it's like a Euler's angle. So if I determine the coordinate by some kind of transformation with respect to the joint angles, this is forward kinematics, right? If I just plug in some kind of transformation with my joint angle in order to determine the coordinate of the n effector, then this is forward kinematics. So I'm gonna call this transformation F, okay? If I try to determine the joint angles with some kind of transformation in terms of the n effector, then is the inverse kinematics. Right? So I'm gonna call this I. Okay? So you know, as human, we usually don't care what is the angle of my elbow. I only care about my hands, where my hands are. I don't care about the body. So you can grab this like this way or this way. It doesn't matter. I just want to grasp this cup. So in human design, or humans' way of thinking, we usually design robot trajectory by the end effector, coordinate of the end effector. That's what's usually happen. But in fact, in robotic control, you're controlling the motor. Okay, so there's always a lot of transformation between the end effector coordinate and the joint angles. So today, I want to share with you what's the usual way, and later on I will teach you one way to do robotics control in an unusual way, and that was done by my graduate student and myself, and that works pretty nicely. Okay, so let's talk about the usual way. So let's say there's one case where we want to move from, since I already use ABC, so I'm gonna say I want to move from a P0 point to some Pn point. Okay, so in the design space, so let's say this is so-called the P0 point, this is the Pn point. If I want to move straight, then in computer, you want the end effector to move straight from a P0 to Pn. So you have to tell the computer or the controller where to go to at the middle. So it's like you are making small cuts. Like this one could be P1, this one could be P2, da da da. I can call this one P, I'm not using I yet, let me call this Pi. So I'm making n points, actually n plus 1 points, because including the P0. So in total, from the beginning to the end, there are totally n plus 1 points. All I need to do is to calculate inverse kinematics for every n plus 1 points. Why is that? So usually from human, we tell the computer these two. So these two are known information. These are like information from the user. You request the robot to move from a starting point to an end point. So those are given information. So these two are given, right? It's very easy to compute the intermediate point on this straight line. It's easy. It's math, right? So those points at the middle, I can call them intermediate points along the straight trajectory can be computed. Very easily, right? Once you have them, what do you do next? You basically perform inverse kinematics for the configuration at that particular coordinate. So you are computing for the configuration for the ith point. And how do you do that? You basically use the inverse transformation. But what do you need to do? You need to do n minus 1 times in total. Totally. n minus 1 times. Because there are n minus 1 points. So it really depends on how many intermediate points you want to decide. What if you only choose 3 points? Then you tell the controller to move from a first initial point to a first intermediate point, and then move to a second intermediate point. Let's say there are only 3. After the third one, you directly go to the end point. In that case, the controller doesn't guarantee between each point it's going straight. So if you do not use enough intermediate points, it could be moving like a wavy curve. Okay, because you didn't tell the controller what are the configurations to be assigned between points. So usually for controllers, if you assign a linear motion, it actually cut this straight line into so many small points and perform a lot of inverse kinematics for each point. So the controller, the computer needs a little time to perform inverse kinematics. Okay? Now, let's think about a different way that could be more effective. So, again, I want to move from P0 to Pn. But in fact, this time, I don't mind if you are not moving straight. Just move the way you like it. As long as you reach at the Pn, I'm okay with it. So a pretty effective way to do it could be like following some kind of curvy trajectory. And I'm gonna tell you what that is. So this is P0, this is Pn, right? What you can do first is to do inverse kinematics. Then you will get the x0. Next, you can perform the same thing for, hold on. My touch panel. Oh, okay. Sorry. Then you can do the same thing for xn, right? So what are the configuration? They are angles. So this is like a theta 1 at configuration 0 until theta 6 for the 0th configuration. And this is like the theta 1 for the nth configuration. And this is the theta 6 for the nth configuration, right? What you can do next is to focus on specific angle, actually each angle. So let's take a look at, for example, the first angle. What you eventually want to do is to start with theta 1, 0, and ends up with theta 1 n. So what you can truly do is, let's say this is time, and this is the start, and this is the end. Okay, I don't know why this is happening. This is the end, okay? And let's say these are the joint angles. And let's say this is my theta, for example, the jth theta at zero configuration. And let's say the J theta at the end is supposed to change to a new angle. I call this theta j comma n. So what you can do is to linearly, oops, I don't know why. Come on, the tip of the Apple Pen is a little bit ruined. So you can linearly change the joint angle from the initial one and reaches to the last one. You can linearly change it. And you do the same for all 6 angles. So by this way, you realize you don't really need to perform inverse kinematics too many times. You only do it once for the first configuration, and then you do it once for the final one. And then you basically figure out how the motor is gonna move. You have a starting motor angle, and then you end up with a final motor angle. However, at the middle, somewhere at the middle, it's gonna be some combination of all 6 angles, but you have no idea how it looks like. So that's why if you say this is a starting configuration and this is the end, you know the joint angle combination at the start, you know the ones at the end. You ask every motor to rotate linearly from its starting angle to the final angle. What you get at the end is some kind of curvy motion. It's gonna be a curvy motion. And you have no idea where those n effector is gonna be, unless you truly compute for the n effector coordinate at every intermediate configuration, unless you try to compute it. And usually, if you have a computer that is working on simulations, of course, simulator will compute for every n effector position at a lot of intermediate points, so that you can see it, right? But in robots, you don't really need a user interface and show you the trajectory. You just need to say, okay, move from here to here with curvy trajectory. And usually they do this, because this is the easiest way. You don't need a lot of inverse kinematics. You guys did homework, right? Inverse kinematics is harder than forward, right? More complex. Forward kinematics is like a plugging in some equation, a bunch of transformation, boom, you get it. But when you solve inverse kinematics, you may have multiple solutions. You need to figure out a way to determine which one is the right one. Okay, it's like solving for unknown parameters. It's more complex. So in this research field, there are people trying to avoid the usage of inverse kinematics. Try to use lesser the better. Okay? Now, once you understand about this, I'm gonna talk about obstacle avoidance. If you have an idea, let's say I want to pick up this phone, and the cup now is an obstacle. So if my robot starts from here, and if I ask the robot to move straight toward the phone and pick it up, I will hit the cup. So the assumption is, for robots, it has to know where the obstacle is. Otherwise, it's very dangerous, because it's a blind robot. It's gonna hit everything the arm swing at. So we usually give the robot its eyes with camera, 3D camera, or a bunch of sensors. So let's consider the problem with known information of the obstacle. Even with known information of the obstacle, if you want to automatically generate a path from the start toward the target without hitting the cup, it's quite troublesome. Of course, there are so many solutions. You can do this, you can do this. There are infinite number of solutions that can reach to the target without hitting the cup. There are infinite ones of them. But for computers, for a practical system, you don't want too many solutions. Just give me one solution. So as a designer, we need to determine what is the most appropriate. So in this research field, there are many algorithms try to find out what is the best trajectory. You don't want to make a large route. Just move closer, make a small route, and then move toward the target. That's usually the best way to do it because you save energy. Think about a robot arm. Whenever you drive the motor to lift the arm, you need electricity. If it's a really heavy robot, you need more power. More power means more electricity. Then that's basically cost. So if you can have smaller movement, you reduce your cost. You don't want to own a company, buy a lot of robots, but the robots are moving in the most inefficient way, which wastes a lot of electricity. Eventually, the boss is losing money. So you want the robots to be moving in the most effective way. Okay. Now, today I'm gonna show you something about realizing how safe your robot is. So while you are moving, you are always evaluating how close your robot arm is compared with basically by determining the shortest distance between the robot arm and the obstacle. So if you hit the cup, you're not safe. If you keep away with a distance, then you're safer. Okay, so it's like a solving for some kind of trajectory with constant calculation of the shortest distance. Okay? First, I think I need to tell you about how to find the shortest distance between a robot. It's not easy, actually. And it takes time. So, if you have a real robot arm, it doesn't look like a simple figure like what I did here. Okay? It has nice geometry, nice shape. Let me try to draw one. Okay? So usually you have a bottom, maybe there's a case. So maybe it looks like this. Usually there's a thickness here. And then you have the other part. Right? So there's geometry. I'm just trying to, and usually there's another portion here. So there's a motor. There's one motor here, right? And there's another motor here that spins in this way. There's another one. There's another one, right? You have done that. I'm not going to finish the whole thing, and it's just ugly hand drawing. But I want you to understand they are arbitrary shapes. And if I have a robot arm made by manufacturer 1, and then another robot arm made by manufacturer 2, they have different geometrical design. So if you truly want to compute the shortest distance from the obstacle to some part of your body, then you are probably evaluating some arbitrarily shaped geometry and then some arbitrarily shaped obstacle. So for example, if I have an obstacle looks like this, some arbitrary shape. So probably in fact the closest point is this tip, and then maybe if you do math, if you precisely compute, there is a projection point here. So it's such a precise measurement if you are truly doing this. So numerically trying to find the pair of points that shows the shortest distance between two geometry, it takes time. Usually it's actually an optimization process, finding shortest point between two objects. That is never efficient. So in research and also in practice, we will try to simplify the model. And when we simplify the model, we will simplify in such a way so we become safer. We don't simplify it so that we could be becoming less safe. What does it mean? And what does it mean by simplified model? Let's say I want to simplify this geometry into a cylinder. Just the smallest cylinder that is containing the geometry. The smallest one, smallest possible one. And maybe for the obstacle, I will consider it as a point. So maybe there's a point. I just consider it as a point with some radius. As you can see, when I do this, I try to find a simpler geometry so later on it's easier for me to calculate the shortest distance between a ball and a cylinder. And when I pick up the cylinder and the ball, I try to cover everywhere of the part, but of course I know I am having some gap between the real geometry and the cylinder. So my cylinder is a little bit wider than my true geometry. So it's not precise. However, it's safe. If the ball, if the ball doesn't contact with the cylinder, no contact, no collision. If the ball have a tangent contact, like a single point contact with the cylinder, even that happens, it's possible there's no collision because my geometry is inside the ball, my robot arm part is inside the cylinder. There is still a tiny gap. Okay, so as you try to find a good trajectory with safe distance, you're talking about safety, right? It's okay to be safer, but it's not okay to be riskier. What is a riskier example? So let's say I have my arms are, affecting the drawing. So same situation, if I have a simplified geometry inside and a simplified ball inside, then when the ball and the cylinder contacts, I already collide. There's already collision. So in this field of research, safer the better. So this is safer, and this is less safe. Okay? So we use simplified models. Simplified models. So the next is to figure out how to compute the shortest distance between a ball and the geometry. So what's gonna happen is, now I have a simplified cylinder. Oh my God. My arm. I don't know what happened to my arm. iPad think my arm is Apple Pen. Right. Okay. And I have a ball, right? So if the ball and the cylinder is in this configuration, the shortest distance probably is this corner point and some point along this straight line. So these would be the pair of contact points, the closest points, and this would be the shortest distance. I'm gonna call this D minimum. Okay, so the key is to find the shortest distance. Okay. However, in some configuration, for example, this is a different example. Now the obstacle probably is here. In this case, you are trying to find the, oh come on, projecting point here and the closest point there. In this case, this will be the D minimum. Okay, so from here you can tell you still need to figure out a way to find the pair of points that indicates the that shows you the shortest distance. Still, it's a kind of optimization process, but we realize we don't really need to. It's a geometrical problem. It's not yet optimization. So one good way to study this is to assign some kind of coordinate system. If I choose the middle point of the cylinder and then I say this is a coordinate called radius. R indicate radius. So this is radius. Basically, radial direction. Oh, come on, man. Radial direction. Okay? And going up, I'm using, what was the coordinate I used? I think I used L. Did I? I need to check my, hold on. I have a PowerPoint. Let me see what I use. I use L, yes. I use the L, okay? Okay, so this is L, and basically this is the axial direction. You know, it's really hard to pronounce AXIAL. In USA, whenever I pronounce it, people are laughing. No Taiwanese is laughing. No one gets a joke. It doesn't sound right. Okay. I'm videotaping myself. I better not talk about that. Anyway, it's a very hard word to pronounce. So let's say I have this coordinate, and I have okay. Basically, the radial direction could be anywhere. I just need to find the radial direction that is pointing at the plane where I see the obstacle. So in fact, if I draw this more precisely, you are having a plane. Come on. I don't know. My hands are super conductive today. iPad believes my hands are the pen. So here's the, come on. No touching. Okay, let me use a book to protect the hand. Okay. Now better. Okay, this is the L direction, and this is the R direction. And let's say the obstacle is on top. On top of the RL plane. So this is the obstacle, and let me choose a symbol Q as the obstacle. So in this case, I have some value R here and some value L here. Okay, so you can say the relationship between the obstacle and the cylinder could be described by this RL coordinate. Okay, and I'm gonna define the radius of the cylinder as, I think, capital R, and the total height as capital L, and I need to describe, let me double check, what did I use? Oh, I use R0, I see. Yeah, that's fine. So, since I said we have multiple joints, and that means we have multiple parts. So let's call this is the Jth simplified cylindrical model. So, in fact, your robot arm will be looking like this. One cylinder, the other one probably looking like this, the third one probably looking like this, another one. So there will be multiple cylinders, and they will be overlapping with each other. It's okay to overlap, because you are basically having a spherical obstacle. You are trying to compute the shortest distance between this guy with this guy, this guy with this guy. You are computing them. You have the d minimum. So let's say this is the j equals to 1, j equals to 2, 3, 4, and 5. So you can call this d minimum 5. This one is d minimum 2. You will have 6 shortest distance between the spherical obstacle and the cylindrical part. You can have 6 of them. So among all these 6 shortest distance, The overall minimum one is the true shortest distance between the obstacle and the entire arm. Okay? So let me define this. The D, oh, come on, my arm. So D, let me call this a D minimum. Just put a star right here, okay? The star represents the overall minimum equals to the minimum of the minimum, comma, J. J goes from 1 to 6. So the smallest one is my overall shortest distance between the obstacle to the entire arm. So now what we want to do is to figure out, this is the jth one. This is the jth one. So I'm gonna call this radius Rj. The radius of the cylinder, I'm gonna call this Rj. And for the spherical obstacle, I'm gonna call this R0. Okay? And then we are trying to determine this D minimum, comma J. Okay? We're doing that. So how do we do that? We can then view this whole thing into a planar way. This is the radius, this is the axial direction, and I can draw something like this. This is basically Rj. This is half of capital L, right? So what I'm drawing right now is this area. Can you tell? Okay. Can you tell? Okay. I'm drawing this pink rectangle. That's basically the pink area on the top in the 3D drawing. Okay. So the obstacle could be somewhere here. That's my Q point. Okay, or anywhere. Now, I have to divide this whole space into multiple regions, and I will tell you why. Now I'm gonna draw some straight line here. Distance right here is R0. This is R0. And here is like a quarter of the circle. Okay? So when my Q point, let me keep on drawing. Let me just draw this straight, like lengthen it. If my Q point is in this region, if my Q point is there, then how do I compute the shortest distance? It's gonna be this, right? It's gonna be that. And actually, because the Q has a, let's forget about the radius of the obstacle for now. Later on, you just need to be aware, okay, the obstacle has a radius. For now, we just consider its center point. So the shortest distance between this particular point and this is like the cylinder, right? It's gonna be the red arrow I have drawn. So what you need to do is, if one day you realize your Q point is within certain region, that distance can be computed like this. Okay, so what is that called? So I'm gonna call this region, do I use the same symbol? I think it's okay. Let me call this region 1, okay? This is also 1. So inside region 1, the shortest distance, d minimum, would be the L coordinate of Q minus a half of capital L, right? So it's gonna be coordinate of L minus a half of L. Why? This is L, this is half of L, so this is small l minus half of capital L, right? So from here you can tell, whenever I know the coordinate of the obstacle, and at certain configuration for the ith part of my body, I reduce it into a cylinder, simplify it as a cylinder, and then of course based on kinematics I know what the cylinder is located and oriented. Compared to the Q coordinate, I will instantly know what would be the R and L coordinate for the ith part. And then I determine where is the coordinate of Q. If it's inside the region of I, the shortest distance is L minus big L over 2. It can be easily computed. So if in another case, if this is region 2, then maybe this is also region 2, what would be the best way to compute the shortest distance? You can choose the corner point. It's gonna be like that, right? If it's inside the entire region 2, the shortest distance is gonna be the center of the sphere and also to the corner of that rectangle. So how do you compute that? Basically, you need to figure out what is this, and then what is this, right? So in the region 2, d minimum is gonna be square root of r minus rj square plus L minus half of capital L square, right? Similarly, if you are in region 3, the obstacle, for example, is here, then the shortest distance is here. In region 3, d minimum is gonna be r over rj. That's it. Right? How about region 4? If your obstacle is inside region 4, your robot is ruined already. Right? But when you are trying to plan the motion, you are planning it with simulations. Before you truly ask the robot to move, you need to complete all the calculations. Since you are doing calculation, then it's possible while you are it's like you are estimating. So without the cup, at some moment, your robot could be having this configuration. And since the cup is gonna be here, you see some part of my arm could be overlapping with the obstacle. So in fact, when you are doing calculation, region 4 is possible. But how do you compute the shortest distance if the obstacle is inside the body already? At least give a value, okay? So in my research, I think I used the shortest distance away from the central axis. I think I used that. You can have different opinion and you can evaluate in a different way. This is not the exact way to do it. This is still a really open research direction. Some researchers do it in this way, some researchers do it in a different way. It's as long as it works, it's a good algorithm. So I'm teaching you what I believe, or what I used. So if the obstacle is inside the body, I think you can use the distance away from the central axis. It's like how far away the obstacle is away from the central axis. That's what I think that's what I used. So in region 4, I think the D minimum I used was R. I think that's what I used. Okay. So you keep on evaluate. It's like at the beginning. Let's say you are doing this. You are moving from P0 to Pn, and you need to check every intermediate configuration. If you are moving straight, then you need to perform inverse kinematics for every intermediate point. And for every intermediate configuration, you determine the shortest distance between the obstacle and that configuration. Okay? So let me write down a procedure, like a general procedure. So the procedure of what? To move from A to B with awareness of collision with obstacles. Oh, by the way, if you have no idea what is this is with, and this is without. This is because. Okay? I'm not kidding. In USA, no professor writes the whole world. No, they just write this. And what is WRT? Who knows what is WRT? With respect to. Okay, what else? I think those are the most commonly used when they write down the notes. Okay, so what's the general procedure? First, you have given P0 and Pn. Okay. Second. Hey, hello, Wilson. If you are moving straight, then you need to figure out P1 to Pn minus 1. okay? And then you need to do inverse kinematics for x1 to xn minus 1. That's for the case if you are moving straight. If you are not moving straight, so I use a two-prong. If you are just having a curved trajectory, then you can directly do inverse kinematics of P0 and Pn. So you will get x0 and xn, right? Then you can compute for x1 to xn minus 1. So you can linearly change the angles. Okay, so either way, step 2, for the step 2, you need to figure out the configurations along n minus 1 configurations. Next, of course, you need to know the obstacle. So you need, given Q is the obstacle, right? Given Q. Now, you need to do some kind, like a for loop. So for each ith configuration, conf means configuration, so first time, so I'm just configure, conf is configuration, okay? So for the ith configuration, so in computer you need to do a for loop because you need to check every configuration. For the ith one, you need to do basically another for loop for basically each of them. The jth body, we already simplify the body into cylinders, okay? You need to evaluate the minimum distance between the jth body and the obstacle Q. You do all of that. So imagine how many calculations you need to do. That's why we don't want this D calculation to be too complex. This is already a pretty simplified way to do it. But actually this requires some kind of coordinate transformation. Because when you are studying this, you need to figure out the center point of the jth body part and what is R, what is L. It also takes some time. You need some kind of transformation. So this evaluation of D minimum is not very straightforward. So what's inside this, there are smaller steps. You need to, let's say you are focusing on the jth body part, so you need to transform your calculation to the R and L coordinate for the jth body at ith configuration. Yeah, as you can tell, it's a lot of them, right? Then in the RL coordinate, you need to figure out what is the RL of your obstacle Q. Because this is my body part, right? Usually you have your analysis in the world coordinate. Everything, the world coordinate doesn't change. However, when you are studying for obstacle avoidance, you need to study on the body fixed frame. So no matter where your robot arm is, and you're studying for, this is the jth body part, you are studying on this body fixed frame. So you need to know how to transform from the world coordinate to this body fixed frame by forward kinematics, because you know at this configuration, you know all the joint angle, you know the geometry, you should be able to find out what is the body fixed frame on the jth body at the ith configuration. Once I have this, I need to figure out in this coordinate, what is my coordinate of the obstacle, Q. So that's another coordinate, because another transformation, because the Q was analyzed in the world coordinate, not on the body fixed frame. So once you are able to transform the body world coordinate to the body fixed frame, you should be able to figure out what's the Q point in this body fixed frame. Okay, that's the tricky part. Once you have it, then from what I show you here, you can easily determine what is the shortest distance between the obstacle and the cylinder. And there are 4 different regions using 4 different equations. Okay? So once you have that, then you can compute for the minimum. And you basically do this repeatedly for every frame, every configuration, and for every body part. Then you will figure out then you know you will get the D minimum with the star. I call this the overall shortest distance for every configuration, because you will, from the for loop, you will get every shortest distance. And for the ith configuration, the overall, where did I put it? D minimum star is gonna be the smallest one between from the shortest distance between the obstacle and every part. You have a minimum distance 1, minimum distance 2, minimum distance 3. You have 6 of them. The smallest one basically is the shortest distance between the obstacle and that particular configuration. You have n-1 configuration. So for every configuration, you know what is the shortest distance between that particular configuration and the obstacle. What to do next? You set up some kind of threshold. How close you can allow. So let me just a brief. So for example, just one example. Let's say, again, this is the this is time, and this is the start, and this is the end. And let's say I have so-called a curved trajectory. So my joint angles linearly changed from the start to the end. So let's say this is my theta 1, maybe my theta 2 is here. Just a random example. Maybe theta 3 is here. Let me just draw 3 of them. And maybe at the end, I need to change my joint angle in such a way. Okay? So I perform some kind of movement from a starting configuration to a final configuration. Okay? And within this trajectory I studied everywhere, and this is like the Jth, not J, ith configuration. I studied the ith configuration. And I realized at this configuration, some particular configuration, and the shortest distance is some value. So maybe the shortest distance is this value. And I keep on doing this, I realize the shortest distance could be something like this. Okay? If I did all the calculation for every ith configuration, and I'm actually being able to draw a curve like this. And maybe, by the way, this is shortest distance. Different unit. Blue one is angle, red one is distance. Maybe there is one allowable shortest distance. So maybe, let me use a different color. Maybe this is the allowable shortest distance. If that's the case, that means within this region, I need obstacle avoidance. So the key of doing obstacle avoidance is that you need to figure out along every moving trajectory at which portion you need to change your coordinate. So always figure out what is the shortest distance between the obstacle and the robot. Okay? Now there are so many different ways to find the newer trajectory so that your robot can move around the obstacle. There are so many ways. Later on, I have a PowerPoint. I want to show you how everyone is doing. I think now is a good time for me, for us, to take a short break. Okay? We didn't stop until we didn't stop for 17 minutes already. So I guess everyone took a lot from today. So let's take a 10-minute break. Later on, I will not do a break. I will keep going. I will go through my slide, and I hope I can finish my slide today. Okay? So let's take a break.